Hello guys. So on the first part of this lecture, we obtained these two expressions right here. Okay, for the density of states as a function of energy in the conduction band. So therefore, for energies above the band edge EC for the conduction band, and the density of states in the valence band for energies below EV, which is the band edge energy for the valence band. As we saw, the distribution of states is not uniform, so this is not a constant. It depends on energy and it grows with the square root of E towards the middle of the conduction band as well as the valence band. So as you got deeper into the band, the amount of states per unit energy grew in both bands. Now we can use this density of states to calculate the actual number of states for any given range of energy values. Of course, it cannot be within the forbidden band, but within an allowed band. So with rho E, we can calculate the number of states per unit volume. Always important to remind ourselves that all of these numbers or these quantities relating to numbers of states or carriers, they are given in units of per unit volume, which means that you calculate the number of states or carriers per unit volume, usually per cubic centimeter. So you're calculating the number of states or carriers in a cube with 1 centimeter on its side, right? So they're normalized with respect to the volume of semiconductor. But if, for example, we want to calculate the number of states available in the conduction band, starting at a lower energy level, E1, up to a higher energy level, E2 per unit volume, we just integrate the density of states over energy between the two limits, right? E1 up to E2. So this is because, as we've said, rho is the density of states, which is the number of states per unit volume, but also per unit energy. So you can think of rho as being the derivative of the number of states per unit volume, number of states with respect to energy. And this follows directly from the definition of the density of states, right? It's the derivative of the number of states with respect to energy, so that if you integrate in a given interval, you will get the number of states within that range. Well, if you want to calculate the number of states in the entire conduction band, you would need to integrate from the lower limit, which should be the band edge, EC, right? You should integrate up to infinity. This would not hold using the expression we've just shown, because we've used the parabolic approximation, which, as we've seen, is only valid for energy values close to the band edge. But for all of the applications considered in optoelectronics, this region has all of the states which will participate in the electronic transition. So the parabolic approximation is a good approximation for all of the applications that we'll consider further in the course. Now, for the valence band, you have the same thing, right? Let's say you want to calculate the number of states in the valence band. Well, you integrate from minus infinity up to EV, the respective density of states, which is rho V of E, the density of states in the valence band, okay? So to illustrate this and calculate the number of states within a given range, let us calculate the number of states between the band edge for the conduction band and EC plus 0.1 EV, 0.1 electron volts, for a non-semiconductor, which is silicon, okay? So we're actually going to calculate this to get a feeling of how many states are available within this range, which spans for 0.1 electron volts. We'll use the fact that the effective mass in the conduction band, the effective mass of electrons for silicon, is 0.98 times the mass of the electron, which is, as we said, 9.1 times 10 to the minus 31 kilograms. Okay, So we just plug in the density of states in the integral and integrate over the given range from EC to EC plus 0.1 electron volts. Now we've just seen that rho C of E with the parabolic approximation was 1 over 2 pi squared times 2 times the effective mass of the electron in the conduction band. Sometimes I write this MC star or ME star divided by H bar squared. All of this inside the parentheses to the power of 3/2 times the square root of E minus EC, right? This is the density of states, the expression for the density of states. If we plug this in here, these two constants right here, this one and this one, can be taken out of the integral, so they will remain outside in here. And you have basically the integral of the square root of E minus EC over the given range. Okay? Here we're just stating again that we cannot use this expression to calculate numbers of states in the whole band or even up to a much higher energy level than EC plus 0.1 because we're using the parabolic approximation and it's only a good approximation for energy values close to the conduction band edge or the valence band edge, depending on which case you're doing. We can solve this by doing a substitution of variables. So the original integral was what? It was a constant times the integral over the range of from EC to EC plus 0.1 electron volts of the square root of E minus EC. D, right? So we can substitute this term right here inside the square root by a new variable u. Okay, so u is equal to E minus EC, and if we differentiate this expression with respect to E, we find that du is equal to dE, so this guy right here can be replaced by du, and what you have is the same constant times, we'll worry about the limits later, the square root of the new variable u du. Okay, so let's see, at the initial bound EC, if we replace this here, you get u is equal to EC minus EC, so giving us u equal to 0, and at the upper bound EC plus 0.1, if we replace it here, EC plus 0.1 minus EC will just give us 0.1. So that's what you get. That's the new integral. Now we just have to perform this integral, right? The constant is this guy right here, 1 over 2 pi squared times this term inside the parentheses to the power of 3/2. And we just integrate now over this new range. So this particular integral is pretty simple. It's the integrand is u to the power of 1/2, so you just add 1 to the exponents and you get u to the power of 3/2, and you divide everything by 3/2, so you get 2/3 of u to the power of 3/2 over the range from 0 to 0.1. Okay, this is the original constant. Now we need to calculate this, and this will give us 2/3 of 0.1 to the power of 3/2, right? Which is what we have down here. You see that the 2 cancels this 2 right here, so that's why you get 1/3. Otherwise, it's the same expression. Now, since the effective mass is given in the metric system, we said that the m star was 0.98 times the mass of the electron given in kilograms. So this will be given in the metric system. We can also use h bar in the metric system. In fact, if we use the mass in the metric system, we have to use h bar in the metric system. And this turns out to be h bar is equal to 1.054 times 10 to the power of minus 34 joules second. Okay, in joules times second. The Planck constant can also be given in terms of EV times second, in which case it is 6.58 times 10 to the minus 15 eV second. And we get this from the Planck constant in the metric system by dividing it by the elementary charge. So if you divide this number by 1.602 times 10 to the minus 19 coulombs, we get the Planck constant in terms of eV times second. Okay. Now, using this and substituting it here, as well as the effective mass we just mentioned, we can calculate the number of states. Now, the only other thing that we need to be careful is that since we're using all of the units in the metric system, we cannot use the energy in eV, so 0.1 would be given in electron volts. We also need to multiply this by the elementary charge to get the energy in joules. So if we multiply 0.1 by the elementary charge, we get the energy in joules. We need to be careful to do this multiplication right here, which is a straightforward calculation that gives us this number right here. So approximately 1.4 times 10 to the 26 per meter cubed. Now it's more usual to give the number of states or even the number of carriers, the carrier concentration, and so on in units of per centimeter cubed. So we can divide this by 10 to the 6th, and we get 1.4 times 10 to the 20th states per centimeter cubed, which is the number of states between the band edge and the band edge plus 0.1 eV. Okay, so this is a very large number of states, the order of 10 to the 20th. But as we said, the number of states in the whole band is estimated to be much larger. We mentioned 10 to the 23 as we have seen. So, 3 orders of magnitude more states in the entire band than you have in the initial 0.1 eV close to the band edge. Okay. Nonetheless, the states occupied in this range. So what I'm saying here is that states, in the range going from the band edge EC up to just 1/10 or 0.1 electron volts up here, right, are the ones occupied when the semiconductor is most heavily doped. So you will not go much further from here. And, these states are also the ones that perhaps, up to 0.2 eV or so, are the ones that are going to be occupied and participate in the electronic transitions as well. So we only need to worry about, give or take a range that is close to this number we've seen. Okay, so we've just finished looking at the density of states. The next thing that is as important as the density of states is looking at the probability of occupation, which is the Fermi function, which is going to tell us the probability of a given state being occupied by an electron or not, which means if it's in the valence band, it is occupied by a hole. And we'll start taking a look at this on our next lecture. So thanks very much for your attention. I hope you have a great week, and I'll see you around.